guess can I just get started?
Sure.
So as I said, I would talk about midterm questions for the most part, and briefly for KKT conditions and interior point if we have time. Interior point and SDP a little bit. So how did you guys do in midterms? The median is 50. The mean is 50.
Percent or out of 80?
Out of 80. That's a good question. Yeah, out of 80.
Okay.
Yeah, 50 out of 80, including bonus points. So because it looks sort of like flat as a distribution. I should show you the distribution, but highest like 71. This is 50. We also get some 30-ish, 40, somewhere here. Yeah, including bonus. Bonus is like 10 points extra. So I guess maybe we will curve the scores. I don't know. So let me just go through them one by one. The first one is to write down the due of a standard LP. And this problem is minimize negative 4y1 plus 2y2, constraint to negative y1 plus y2 greater or equal to 2. Okay, so how can we solve this? We can just follow the standard procedure to find the due problem. First step, we write out the Laplacian. Sorry, keep saying this. First of all, we write out the Lagrangian of this problem. And the Lagrangian is composed of the objective function and the Lagrangian multiplier times the constraints. But the constraints needs to be something smaller or equal to 0. So that's the place where you could get wrong. So minus or plus. So I'll write this one as constraint x1, x2, and these ones x3 and x4. So the first constraint, the first multiplier times, I want the negative sign, so this is 2 plus y1 minus y2. I already understand why I have plus y1 minus y2. Right? And similarly, I had this 1 minus y1 plus y2. And for the last two inequalities, I got this wrong. It should be minus x3 y1 minus x4 y2. Okay. And step 2, solve for primal. So minimize primal variables, which is y1, y2 of this Lagrangian. And this, how can we do this? So we organize terms for y1 and y2, and we let the coefficients for these terms 0. So for y1, this is negative 4 plus x1 minus x2 minus x3. This is the coefficient for y1. For y2, it's 2 minus x1 plus x2 minus x4. This is y2. And we also have some constant terms. We have 2 times x1 plus x2, right? And the minimizer of this one is, because all the x are, the y terms here are unconstrained. So if the coefficient is not 0, the y variable can always find a way to make this term negative infinity, right? And how we write negative infinity is negative I, for example, this one. Negative 4 plus x2 minus x2 minus x3, 0 equals to 0. So this indicator function indicates that if this constraint is satisfied, then we have 0. If it's not satisfied, we have negative infinity. Okay, so this is the due problem. Maximize over x, which is characterized by this constraint and this second indicator. Plus the constant term. Finally, we can simplify this by creating feasibility constraints to these terms, because otherwise the g function will be negative infinity, and that doesn't help the maximization problem. So you can equally write the due problem as max x, the objective, and the constraints are this is 0 and 2 minus x1 plus x2 minus x4 is 0. And I forgot to mention that you actually require all the multipliers to be non-negative because they correspond to inequality constraints. So then I have x greater or equal to 0. And if you look at this, you'll find out that x3 and x4 are slack variables. And really what you need is these part needs to be greater or equal to 0, and these parts needs to be greater or equal to 0. That's the due problem. Let me check if I had everything correct. Okay. So the second question is, what is the duality gap? So if you observe the due problem, you find out that here you have the first constraint is x1 minus x2 needs to be greater or equal to 4. Second one reads x1 minus x2 needs to be smaller or equal to 2. This is x1 minus x2 is greater or equal to 4. Right? These are equivalent constraints. And you can see that these constraints cannot be satisfied. What that means is that you can't have these two established at the same time. So the due problem will always give you a negative infinity. So for every, because it's infeasible, the due problem, the due optimal d star is defined to be negative infinity. And this is a consistent definition because here you have always negative infinity for every x1, y1, x1, x2, x3, x4 greater or equal to 0. Similarly, the primal constraints are also not possible to be satisfied. So primal problem is p star is plus infinity. Just by analogy, you have negative infinity here, you have plus infinity here for infeasible problems. So then the duality gap is infinity. That's the answer. Okay, so any questions? Okay, so second problem is convexity of 4 equations. First one is this. And what you do to find out the convexity is, this is a differentiable function. You just take the second derivative of this function. The first derivative is 4x third plus 2x minus 1. And the second derivative is 12x to the second plus 2. So you can see this is not only always greater than 0, but also greater than finite bound. So we say this is strongly convex because it is lower bounded by a quadratic function. Okay. Second one. So strongly. A lot of people get this wrong, by the way. Okay. This is the second equation. The second function. And the second function, if we plot it, you notice that, well, this is not necessary, but I just found it useful. When x goes to negative infinity, this term goes to 0. And log 1 is 0. So in this end, you have 0. On this end, when x goes to plus infinity, extremely large, this 1 doesn't matter, because ex is substantially greater than 1. And if you remove this 1, you get x. So asymptotically, it converges to this y equals to L. This is y equals to x curve. And this is the shape of the function. Okay, from this function, you can see it doesn't have it is a convex function, it seems to be. And it seems that there's no quadratic lower bound for this function. And it turns out to be true, because if you take the second derivative, first derivative reads like this one. And also, by the way, this is logistic regression, so you should be familiar with how to take the second derivative of this function, because you might encounter it later very often. Second derivative is, first you take the derivative of the numerator, then you take the derivative of the denominator, which is squared, so you have negative sign here, ex, and you take a derivative for this term, so that is ex, another ex. And then you merge the two fractions. You get ex plus e2x for the first fraction minus e2x. And these two cancels. You get ex on the numerator and 1 plus ex squared on the denominator. Denominator. Sorry. Okay, so this is greater than 0. That's fine. It means it's convex. But you can see as x goes to negative infinity, what will happen is that this will be 1, right? E negative infinity is 0, right? Remember, the function of ex looks like this. It's 0 in the negative infinity. So this is 0, this is 1. You get 1 in the denominator. You get 0 on the numerator. So you get 0 curvature towards that end. And to this end, if x goes to plus infinity, this 1 doesn't matter. You have 1 over ex. And again, it will go to 0. So you have 0 curvature on this end and 0 curvature on this end. It cannot be supported by a quadratic function on the entire domain. Well, it could be lower bounded by a quadratic function on a fixed interval. But you want this to be applied to the entire domain, and that's the point for convex, for strong convexity. So it is not strongly convex, it is strictly convex. It's always greater than 0. Strict convexity is to guard you against something like this. You have this is not strictly convex because you have a linear plane. And the derivative is not 0, but the second derivative is 0. There's no curvature here. That is what strictly convexity guarantees you. You don't have something like this. Okay, and for the third one, I take the third one, the function is y minus ax squared. The third function requires that n is greater or equal to p. And if you look at this shape, you find out that y is like n-dimensional. So y is like a very tall vector. A is m by p, which looks like this, and p is a shorter vector. So this is how these vectors and matrices look like. So because there are more constraints than your variables, this one usually is strongly convex. It's over-constrained problem. It's over-constraint means good. Under-constraint means you might need a sparsity constraint or something. Over-constraint means you can always solve it. And the way to prove this is strongly convex is you take the second derivative of this function. The first derivative is, you should be familiar with this, A transpose AX minus Y. The first derivative. The second derivative, or the Hessian, there's a 2 here. Second derivative is A transpose A. And because A is, I said A is M by P, A transpose A is P by P. And A transpose A is full rank. It's positive. So A transpose A is positive definite because it's full rank. First of all, it is positive semi-definite because of the shape is A transpose A. So for any X transpose, A transpose AX, this will always be greater or equal to 0. And also, it's full rank, so you don't have 0 eigenvalue. So it is positive definite. And that's also why the Hessian is always positive definite. You get strong convexity. It's not only positive definite, but also positive definite positively greater than a constant bound. The smallest eigenvalue is greater than some constant, and it's greater than 0. In practice, you want this constant to be big so that your underlying quadratic form is also like growing quickly. If this is very close to 0, even if it's constantly greater than 0, it's not really helpful because it's growing very slowly. That means your why do you want something that grows quickly? That means something growing slowly means slow convergence. So the last question is the case when n is smaller than p. Then this is p by p matrix, but it's rank n. So it cannot have it must have 0 eigenvalues. And so the minimum eigenvalue of A transpose A is 0. In that sense, it's only convex. It's not even strictly convex. So it also means taking some proper affine transformation of your variable, you can get something. For example, if you define y to be ax, then on this y domain you can get, I don't know, if this is y1, this is y2, you can get something that looks like a quadratic on y1, but it's constant on y2. In that sense, you cannot optimize the function along y2 because it's a constant. Okay. Okay, so let me go to the third question. Third question is actually, I guess, an easier one. It asks, whether this set is a convex set. This set is X in R2, X1, X2 greater or equal to 0, and X1, X2 is greater or equal to 1. The third question. So my first step towards this question was to draw a picture. So on one axis you have x1, on the other axis you have x2. So what this says is x1 times x2 is greater than 1. So if you take this is x2 equals to 1 over x1, the convex set is this shaded area. And that could indeed be a proof, because 1 over x is a convex function. You can see from the shape, the curvature is always this way. So this is a convex function, and the AP graph of a convex function is a convex set. That's the proof. That's one acceptable proof. Alternatively, you can do algebra. Basically, if this is some point x, if this is some point y in the set, you want to show that any combination, linear combination, lambda x plus 1 minus lambda y, for lambda smaller or equal to greater than 0, smaller than 1, you want to show this point is also in the set. And the way to show it is basically to show that lambda x1 plus 1 minus lambda y1, which is the first coordinate of this point, times the second coordinate, lambda x2 plus 1 minus lambda y2. This is greater or equal to 1. This is what we want to show, alternatively, algebraically. And the way to show this is through Cauchy-Schwarz inequality. So first step, you expand the bracket. This becomes lambda squared x1, x2 plus 1 minus lambda squared y1, y2 plus some cross terms. The cross terms are lambda 1 minus lambda. You have x1, y2 plus x2, y1. Okay? And by Cauchy-Schwarz inequality, this is greater or equal to square root x1, x2, y1, y2, 2 times these. And remember, x1, x2, y1, y2 are non-negative. So you have these. And then you complete the square. Right? You have lambda squared x1, x2. This is your a squared. This is your b squared. This is 2 times ab. So you complete the square. This becomes lambda times square root x1, x2 plus 1 minus lambda square root y1, y2. 1 minus lambda square root 1 y1, y2 squared. And because this is positive, non-negative, this is non-negative, these two are greater or equal to 1. So the entire thing is greater or equal to 1. That's the algebraic proof. But intuitively, this is what it's doing. So just, we only have like 5 people, so just ask me any questions you have. There isn't much to say about this problem. The most thing you can get from this is how to relate a convex function with the convex set. The EP graph of a convex function is a convex set. The simplest way I would go. Okay, then we have this problem of first order methods. So a definition of first order method and second order method. So it's saying, the question asks, suppose I have a convex function and I have a starting point x0. At every step, so first order method is defined for any algorithms if it satisfies this constraint. So the constraint is xk at the k step has to be in the span of all previous steps plus x naught. So this is the definition of first order method. And I believe in class we showed there's a theorem saying that for any first order method, the rate cannot be, for any first order method, for any smooth function, smooth convex function, the rate cannot be better than 1 over k. I think that's the rate. Anyway, we have a counter example for to demonstrate that any first order method cannot be better than 1 over k rate. Okay. And why we want this to be the definition of first order method is that we could have different first order methods, but this is just a more general definition for first order methods. And the problem asked first whether gradient descent is a first order method. And apparently it is, because the step is at xk is x at xk minus 1 minus some step length times the gradient at the last step. So as long as xk minus 1 is in this span, in the span of the previous j smaller or equal to k plus 2, k minus 2, then this whole term should be in the span of this gradient of f to k minus 1 plus x0. Okay. If we also write out, the second part is whether Newton method is a first order method. So Newton method update rule has this Hessian at step k minus. So Newton method has this Hessian multiplier, and this is a Hessian matrix usually. So this is a matrix. It changes the coordinates, and generally you can't stay in this span generally. So for example, if we are doing quadratic programming, if the objective looks like, I just had a numeric example, but the picture looks like this. So suppose this is a two-dimensional plane, and your function is defined on R2. The level map of your function is like this, quadratic function. So maybe this is f equals to 1. This might be f equals to 0. No, you don't have 0. So maybe this is 1, this is 2. And this point is f equals to 0 where you want to find. Okay. And you're starting from 0. So first order method will search along this direction. And by definition, it means that your step can only your first step can only land on any point along this line. But our second order method for quadratic programming, it will directly go to the center. And the center is not on this line for this particular problem, right? Because quadratic programming looks like x minus b transpose a times x minus b. And the hashing of this is, so maybe there's a half. The gradient of quadratic programming is a times x minus b. The hashing of this is a. So the inverse of hashing times gradient gives you x minus b. So your second step is x minus a inverse a times x minus b, which gives you b, which is exactly the minimizer. So you just hit on the target at one step. And this target, if this target is not on this span, then it's not a first order method. So a related method is called a coordinate. So the disadvantage of a second order method is you have to evaluate this hashing. And if you're optimizing a lot of variables, then this hashing could be very large. And it could be expensive to invert this hashing. So to improve this, you can have a coordinate descent, which is often also referred to as 1.5 order method. Because it is second order method on every coordinate. But it works at the one coordinate at a time. This is a coordinate descent. Alternatively, you can have a quasi-Newton method. You don't actually compute A inverse, but you approximate A inverse using rank 1 update or rank 2 update, a faster algorithm. Okay. So next question is Newton's method. This one, I think we only seen very few correct answers, 5 or 6 correct answers. The question asks, if I define sigma k to be xk minus x star, epsilon k to be this, then if I'm working on one-dimensional functions, and if I have these constraints, so here it says it is a strongly convex function, and here it says the Lipschitz, the second order Lipschitz condition. This is like a second order Lipschitz condition. And this is constrained on a set x for any x belonging to set AB. You want to show the error at the next step is bounded by the error at the current step. So this also means you have log convergence. Is that? So if you show this convergence rate, then you can get something like log sigma plus 1 smaller than some constant plus 2 times log sigma k. Right? Let me see. But sigma k is smaller than 0. So sigma k is, so suppose sigma k is a very small number on the log scale. So this is log. Sigma k is somewhere here. Okay. So it says if that is satisfied, then basically at every new step, this is smaller than 2 times this log plus some constant. So I guess it means you're converging very quickly. And it wasn't really clear at this time, but I think this basically shows that you have a log scale convergence rate. That's the point of this problem. And how can we show this? So without knowing anything, we write out the Newton method update rule. And this worth 3 points because I graded this question. Inverse G prime xk. This is update rule. Okay? And I want to change this variables to epsilon. So I subtract x star at both sides. I get the change in my error. Now what we do, we already have something about G double prime, but we don't have anything about G single prime. So we want to address this G single prime. What do we know about G single prime is that the derivative of this function is 0 at the optimal point. So we know G prime x star is 0. And by the way, this is also worth 3 points, I guess. Okay. We know G prime of x star is 0, but we don't know G prime of xk. So natural thing we can do is to approximate G prime xk from G prime x star. And that's exactly what we do. We write out the Taylor expansion of G prime xk on G prime x star. So first order derivative of G prime is G double prime. G double prime x star xk minus G x star plus a half of the second derivative of G prime, which is G triple prime x star xk minus s star squared. Any questions about this Taylor expansion? We could also reach this Taylor expansion from the Taylor expansion of the objective function. Basically, if we start from this one, I guess I saw 1 or 2 answers starting from here. Plus a half G double prime x star plus 1/6 G triple prime x star. Oh. Oh, I have to correct myself a little bit. So I actually wrote exact equality here. So this one is not really x star, but something lying between xk and x star. So because I didn't write little o for the remainder, so to correct that, I have this G triple prime evaluated at some point between xk and x star. And then I can make this exact. Also here, this is a variable between xk and x star. But it's fixed once I know xk and x star. And this value is found from, I don't know, Cauchy median number theorem, something like that. I am studying calculus. So basically, if you have a function, any function, continuous differentiable function. And you always can find some point where the slope is equal to the line segment. So in this case, you can find 2, whose slope is equal to this slope of the line segment. And similarly, this is how you find this variable c, but you don't work on the first order derivative, but you work on the third order derivative. Okay, and if you start from the Taylor expansion of the function value, the next step is you can take a derivative of xk. And if you take a derivative of xk, this term becomes g prime xk. Okay. And here you get 0 because it doesn't have xk. Here xk is a scalar, so so you get g prime x star. And this is a square, so so you follow the rule of square. You get g double prime x star xk minus x star. And here you have a xk minus star to the third, so you follow differential rules to the third. You get this term. Basically, you get the same Taylor expansion. Okay. Dot, dot. So we have the Taylor expansion, and then we can properly approximate g prime star, g prime xk, which is, as I said, the derivative at x star is 0, so I can get 0 plus g double prime x star. Xk minus x star is epsilon k plus I have g triple prime c times epsilon k to the second. We also have the update rule, which says epsilon k plus 1 equals epsilon k minus g double prime xk inverse g prime xk. So we substitute g prime xk by its Taylor expansion. And I'll just erase g prime xk and put in g double prime x star epsilon k plus g triple prime c times epsilon k squared. Okay. And you open this bracket, you get epsilon k minus g prime xk. All right, this g double prime xk, g double prime x star epsilon k minus g double prime xk, g triple prime c times epsilon squared. So we're almost there. The only thing is here we have g double prime of xk, x star, here we have g double prime of sk. And actually what we want to do is, you already see things that you want. I have a g triple star of any x is smaller than c2, so I have c2 here, I have c1 here, and I lost this 1 over 2, so I make it here. So you get the correct term, you get the correct form on this part. The only thing you need to do is to cancel out the first two terms. But I guess it's hard to do. One way, So basically, when I was writing on the scratch page, I just claimed victory at this step. But when I'm showing it on the board, I just realized that you have this discrepancy. One way is that you can expand, instead of expanding g prime xk at x star, you can expand g prime x star at xk. If I just swap all these, if I swap this with x star and this with xk, this one with xk, this one also, I change another c, but I don't change the notation. But I get another correct expansion. Maybe I also want to revert the sign here. This is negative ck. And I get 0 here. So I still can replace g prime xk with these two terms. And I get g double prime xk here. Everyone following? This is the correct solution. It just occurred to me, maybe there's another workaround. Maybe we can, I don't know, maybe we can expand g double prime xk near g double prime xk, right? And you have a g triple prime xk times x star minus xk. This is not xk, but another variable between x star and xk. So you can also substitute this g double prime xk x star with these two. So if you do that, then this one cancels with the denominator, and this one gives you the same thing as this part. I guess the only difference is you lose a constant factor. By this way, you only can get, I don't know, 3/2 constant factor. If you take the original approach, you can get 1/2 constant factor. The reason I say it's 3/2 is because this is g triple prime eta, this is g triple prime c, and I don't know anything about these two, except that they are all absolutely smaller than c2. So if I substitute something like this, I will lose a factor, but I get the same order. Is there any question about this problem? No? Okay. The sixth problem is optimality condition. Let me erase this real quick. So it asks if you have a problem that's, I don't know where this problem comes from, but I bet from the notations, it's probably coming from the Steve Boyd's book, Convex Optimization. Because here he uses these notations very often. F0 is your objective, and F1 through Fm is your constraint function, are your constraint functions. Okay, so it asks, you to prove this greater or equal to 0 for any feasible x. So what this means, suppose you have a function f, I don't know, maybe a linear function. So maybe this is where f0 is 1, f0 is 0, f0 is -1. So you see, you get the idea. This is a function, a linear function. So how can you say you find optima? You have one constraint that looks like this, maybe. Okay, this is your f1. f1, 0 equals to 0. You get this. And maybe this is where f1, 0 equals to 1. So instantly, you know the optimum is here. Because here is the feasible point where f0 is the minimum. Departing from this point, you reach somewhere that is not feasible. Let me see. So at this point, you get a gradient that's there, right? So do you get 0 gradient on this on your objective function? So is this gradient f naught at x star 0? No, it's not. It still has a valid gradient. But what happens is that its gradient collides with the gradient of the objective function, of the constraint function. Judging from the shape, this is f1 x equals to 1, this is f1 x equals to 0. You probably say that the gradient of the constraint function also looks like this. So, I need to backtrack. The gradient of f naught is the opposite direction because you want to walk on the negative gradient. So what you can conclude about the optimal point of the constraint problem is that instead of having 0 gradient on your objective function, but your objective function is a linear combination of your constraints, the gradients on your constraints. So the gradient on f1 is this, and the objective function is some number times the gradient of this. This is something lambda times this. For example, at another point, you know this is not the optimal point because the gradient of your constraint looks like this, but the gradient of the optimal function looks like this. So you can still find somewhere to go that is allowed, right? If you find out the perpendicular line to the gradient of the constraint, you can walk approximately along this direction. And then your objective function is still decreasing while you are not violating your constraints. That's also the motivation behind the KKD condition. The KKD condition says that the gradient of the stationary condition says that the gradient times lambda times lambda multiplier times f1 0 x, it has to be 0 at the optimal point. Right? You see where that comes from, the stationary condition. Also, this is Lagrangian multiplier. If you're minimizing a function in under some constraints, you always put a Lagrangian multiplier, and you minimize the Lagrangian. Okay, so that's also why we have a hint here saying you need to use the KKD conditions. Let's see if I can see anything here directly. So now you have now you are reaching at your optimum point x star. For any feasible point, this direction has to have a positive projection on the gradient of the function. You can see it very clearly on this picture. You can't have anything lying here. And you can think that maybe it has something to do with the gradient of the constraint. So rigorously, how you can solve this is to start from the KKT stationary condition. So from the stationary condition, you get that equation, and you can multiply x minus x transpose on the left to get this times f naught x star plus. So you multiply x minus x star transpose to the left of every term, and you move the second term to the right. So then you get negative. So for simplicity, let me just write one constraint. Lambda subgradient f1 x star. So this is the KKT, what you can get from the KKT condition. Okay. Sorry, I have to write many of them. So there's actually a sum for all I equals to 1 to m. Now, suppose I have another constraint that looks like this, some weird shape. That's not a convex constraint. Sorry. Suppose I have something that that looks like this. Okay. So this is f2, 0, and maybe this is f2 equals to 1. This constraint doesn't matter what happens on this boundary. In KKT condition, what you can tell is lambda 1 is greater than 0 because it's the boundary. This is a constraint that actually matters. But lambda 2 is 0 because the gradient of f2 is never considered because f2 is never relevant to the problem. So that's also why we have this primordial slackness condition in the KKT conditions. And also, that's also part of the proof we need here. So that proof is, if I continue from this equation, only those active constraints matter. So I'll simply write I belongs to active. Lambda I, maybe I should write a star here. That's really the Doom optimizer. Lambda I star, separating fi x star. Am I losing something? Yes, I lost this transpose. Okay. So algebraically, I want to express that my x is in this feasible constraint. That means the projection of this point onto the gradient of the constraint is negative. That's what I want to express next. So basically, I have fi of x is greater or equal to fi x star plus x minus x star transpose gradient of x star for any active. This is true for any I, but for active xi, I also have this one is smaller or equal to 0. This is also true for active. So anyways, this holds for all the constraints. The next step is really just to move things around. So for active constraints, I have these equals to 0 for active constraints. So then you can see this term, which is also what we need here, is smaller or equal to 0, that means its negative is greater or equal to 0. Any questions? No? So next question, question 7 is conjugates and subgradient. This is rather, this is a nice question, but rather a question testing the concept of subgradient. So to remind you, this is the definition of conjugate function, max over x. And you're assuming f double star equals f, you're asked to prove the equivalent of this and this. Did you all get this question correctly? I should have asked before every question, so I know like how much I should go into. Oh. Okay. So the proof is really just comes from the definition. Let's see. We have the conjugate form. So we want to express what is subgradient of f star x, f star y. And we've done this many times in homework, in class, in recitations. So you view the right-hand side as a family of functions parameterized by x, right? F star y is a maximum of a family of functions. So the subgradient of x star y is the subgradient of those single functions which maximizes which attains the maximum. So that means rigorously, the subgradient of this is, first of all, it's a convex closure of all these functions which are parameterized by the parameter x that maximizes the function value equals max. And you want the subgradient of every single function. You get this? This is the definition of a subgradient over a family of functions. Okay, then this is equal to convex closure of union still this x. Let us over x. Let us evaluate this subgradient of every single function parameterized by x. So you can see this subgradient is simply x, right? So then you get, basically, if I write it more prettily, I get the union of all such x such that this x maximizes this function. So maybe here I should write maybe S just for disambiguity minus Fs. Okay. And the next step is I want to quantify this condition. So what do we know about parameter x that maximizes this family of functions at this fixed y? So y is given. What can we know? What s that maximizes this function? So I want to find out what x are actually in this set. So how do we find out that? We take a derivative. Whatever maximizes this this thing has to be the derivative of this thing respect to s. So basically it says that this has to be 0 if x lies in this set. So if evaluating this equation, you get y minus, sorry, this should be, I should use this symbol instead of equality because I'm actually taking the subgradient. So here you get equivalently y minus subgradient of x has to contain 0. That means y has to be contained in subgradient of x. So that is a necessary condition for x to be included in this set. Let me think. So this is part of the subgradient, okay? And this x has to satisfy these conditions. But also we know, because f double star is f, we know that f is a convex function. And this is all convex function. And a convex function can be maximized if and only if the subgradient is contains 0. So this is actually bidirectional. So now what we can say is whatever x that makes this happen can be an element in this set and can be an element in the subgradient of f star y, partial f star y. So basically we have proved that y belongs to subgradient of x star leads to x being in subgradient of y star f star y. And we also need the other direction. That has to come from the other duality, which is, we also know f double star x is maximize of y of x transpose y minus f single star x. Did I f single star y? This is the definition of y f double star x. So from this, forming a similar argument, I can get x belongs to, so I replace x with y, I replace f by f star. This leads to y belongs to subgradient of f double star x. And finally, I use f double star equals to f. I get both directions. Okay, so when we have this barrier method problem and the last bonus question. Yes, I'm going rather slow. The barrier method problem says, suppose you have a barrier function b of x, and you have a set of multipliers. Okay. And for every weight, you get a minimizer x star. You have a feasible set here, fx plus 1 over ck bx. Okay, and you want to show bxk is smaller or equal to bsk plus 1. So let us draw some pictures. So a requirement for a barrier function is that bx has to be greater than 0. Is that part of the requirement? I don't know. Let's see. So suppose we're doing it in one-dimensional x, and this is my feasible set S here. I'm only worried about this end. So now my barrier function might look like this. This is b of x. Maybe this is, let me draw 1 over ck bx. Okay. And let me just draw it more exaggeratedly. So maybe this is ck plus 1. Let me say that this one is 1 over ck bx. So as k becomes larger, this function gets more closer to the actual rigid boundary. And your objective is something like this. This is f of x, right? You want to minimize towards this direction. So without any constraints, the x will always go here, 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 and go to the plus infinity. But with some constraint, you can't actually go to infinity. So what will happen is it will find the optimal point. So here, if I draw negative fx, so because whatever minimizes this has to cause its gradient to be 0. And the gradient, one way to show that the gradient is 0 is that the gradient of x, fx is the negative of the gradient on this part. So the negative of fx, which for simplicity, I just used a linear function, linear objective. So that means the gradient of negative fx has to meet the gradient of b, this 1 over c plus 1 bx. So we are here. For the other one, we are here. So several conclusions we can draw is that whenever ck becomes larger, the optimal solution gets closer to the boundary. In hard constraint, we have this exact boundary. And also, what we're asked to prove is B of ck is smaller than B of ck plus 1. And that is also true because the function bx is increasing towards the boundary. So as you get closer to the boundary, the function value becomes larger. So mathematically, actually, the proof is simpler. So mathematically, what you only need these two equations. You need that for the kth problem, this is your minimizer for the kth problem. So it should be smaller or equal to any arbitrary number, including the minimizer for the k plus 1 problem. On the other hand, the minimizer for the k plus 1 problem has to be smaller or equal to any arbitrary number for this k plus 1 problem. And you add these two up. You can see these two add up. So you add, and these two, and this pair cancel. So you get 1 over ck bxk plus 1 over ck plus 1 bxk plus 1. This is smaller or equal to 1 over ck bxk plus 1 plus 1 over ck plus 1 bxk. Right. This way you have this aligned multiplier and optimizer. This part you have a misaligned, and you just basically you would move this term, which contains xk, to the left, and you would move this term to the right. And you can see here you have xk minus ck minus 1 over ck minus 1 over ck plus 1. And on this side you have 1 over ck minus 1 over ck plus 1. So these also cancels, so you get bk bxk smaller or equal to bxk plus 1. Any questions? So I guess I don't really have time to go over the bonus question because we have another class in this classroom at 6. But I guess it's pretty standard to show how to work out. You just follow the standard procedures for the bonus question. And yeah, I can post the answer to the bonus question later in Blackboard. But it's a pretty standard thing to do. So yeah, so to finish off, let me just use several sentences to comment on KKT condition interior point method and SDP. Okay, so I wished I have this plot, but this is a really nice plot. It basically characterizes what we can expect from KKT conditions. And if I summarize the KKT condition, so by the way, you can look up everything in Steve Boyd's book, Convex Optimization book. So let's see. Maybe I should really. So, anyways, so for KKT conditions, you have a constraint that says, oh, come in. Sorry. Yeah. We're over. Yeah. Come in. We're over. So I don't know. I have to go like this. Sorry.
Exactly, yeah. I'll tell you if I did something wrong.
Excuse me, can I get my camera there? Yeah.